Record. So in this section, in section 3.3, notice, by the way, this is corresponding to your book, right? 3.3. So I'm not going over 3.1 and 3.2. This is just 3.3. Okay, we're just going to 3.1 and 3.2 was all the trig that I've been teaching you in the last, few days, that kind of stuff. That's really what goes on in 3.1 and 3.2. So we're going to spend today, we're going to spend tomorrow, Friday, Monday, probably like 4 days on this section alone. Okay, there's a lot to do with it. Your next test, when is your next test? Anybody have it actually open? October 21st? Is that right? That sounds really far. I think that's too far. That sounds right?
It's like 1 month, yeah. I think you said
you have it?
June 8th or something?
Oh no, 21st. Okay, you know why? I forgot because there's the 4 days of Kairos that aren't in school, so I counted for that. So your next test, I'll tell you now, will mainly be this section and probably the beginning of chapter 4. Like 4.1 and 4.2 most likely. But it's going to be a lot on projectiles. Okay, there's going to be a lot of work on this. Do I have you guys for a double tomorrow, or is the other class double tomorrow? No double for you guys tomorrow? Okay. So your lab will do on Monday. And we're going to do a lab on the computer with projectiles and moving and looking at the angle and change.
Our double's on day 3.
Day 3. They're day 1. That's what it is. Okay. So we've got 3 objectives. First, we're going to recognize when an object is moving in some sort of parabolic pattern or a projectile. Understand the path. And then the third thing, resolve velocities into components to solve by component-specific equations. Okay, and I'll explain what I mean by that in a moment. Okay? So, a projectile is simply defined as any moving object that can be modeled as a point in space. What I mean by a point in space is this. If a rocket is launched, you're not looking at the whole rocket really, right? You're looking at the rocket and you're saying, okay, well, let's look at the center of the rocket, or what we call the center of mass. And then as a result, we can travel or track the center of mass. So the person's center of their body is what we're looking at here. Maybe like, see where the person's belly button is? That's where you would consider that to be like the point. So this is the person's, center of mass right here. And then when they jump, now they're suddenly a projectile. Okay, because they're moving in 2 directions. They're moving vertically and horizontally. So projectile motion here, when we're looking at this, is 2-dimensional motion. It's also free fall with horizontal velocity. So what I mean is this. If an object is only launched horizontally, it's considered a projectile still, because over time, it will start to fall like this. Imagine you have a cliff, and an object is launched off the cliff like this. It looks like it's only horizontal motion at first, but the path that this will take will be this. So in the end, it will be parabolic, it will be projectile motion, although initially it may seem like it's only horizontal motion. Josh, so the path of a projectile that it follows, we said again, is parabolic. Now, what do you think this is trying to illustrate? What do you think the black versus the blue dashed path is trying to show that we could have? Okay, so if it's a higher angle, maybe it follows that higher path. What else? There's many answers that you could think of here. Okay, the motion that you theoretically, not optimal, but theoretical motion versus what actually happens. That's what I was thinking about, and I'll explain that in a minute. What else do you think of when you see this? Somebody heading the ball, yes. Maybe the position, hit them on the head, right? Hit them on the top versus the front of the head, it will go differently. Now, what I wanted to just go over real quick is that the realistic path would be the black dashed line. But in class, what's that? They're both with gravity, because they're both falling. But the black line includes what kind of resistance? Air resistance, okay? So what we're going to do in physics this year, which you're going to do pretty much in all physics courses until you learn calculus, is we're going to assume that there is no air resistance, or it's negligible. So the path traveled without air resistance is the blue path. Okay, the blue path is without air resistance. The minute air resistance is encountered, it's going to automatically slow down the object. It's going to slow it down so that it would follow that black path right there. Now, if we think about this, realistically in life it's not true. And in life you can have a wind that helps you or a wind that hurts you. If you ever kick a soccer ball before, I use soccer because it's a great example, baseball not as much. But a soccer ball, on a really windy day, as a goalie, you always want to keep your kicks down, because if you kick it higher, there's more wind up in the air as you go higher, and suddenly if the wind is against you, you'll kick it and it'll start coming back. It'll drift backwards. So versus, if you keep it low, it won't get affected by the wind as much. So the wind can act against you, or maybe the wind is behind you. And in that half, as a goalie, you know what, I'm going to put a little bit of air underneath it so the ball will carry further down the field, maybe, depending on what your desired goal is in that problem, or in that play. But remember that air can help or hurt you. We're going to assume that it doesn't do either. Okay, that it is negligible. Whenever I say negligible, I mean it doesn't really affect the problem that much. Okay, it doesn't really have any major impact on the problem. Okay? Alright. Let's take a look at this next thing now. And this is where we get our idea of objects launched horizontally. And I need to do a quick little demonstration, so I'm going to steal your desk, Josh and Jen, if you don't mind. You can leave your calculators just moving for now. I'll do this. This is your science. So keep a flip engine. Just click that up. Alright. Two people want to volunteer to do something? It's very simple. Mike, come on up. Jake, come on up. Sorry, Josh. So that first. Alright, one. Jake. Okay. Now, here's what they're going to do. One of them, it doesn't matter who, because you're over there, you can be this person. So what Mike is going to do is Mike is going to roll the tennis ball off the table. Okay, he's going to take this side and just roll it, and it's going to fall off here. What Jake is going to do is Jake is going to wait right here with this tennis ball. And as soon as that tennis ball leaves the table, he's going to drop his. Okay? And we're going to hope that we see something interesting happen. Back up a second, actually, so we can see all of it. Yeah, so what I want you to do is this. I want you to stand back here. Okay? Hold the ball on the table for now. And imagine if you were just going like this, but keep it at the exact height of the table. So don't move the height, like right there. You see what I'm saying? So hold it down and just slide it over a tiny bit till it's off the table. Okay, now wait there. Is he lined up with the table? Is the bottom of the ball lined up with the table? A little bit higher? Okay, and now move left a tiny bit also. Okay. So, as soon as that ball gets to the position right here where it starts to fall, you need to let go of that.
Yeah.
Make sense?
Yeah.
Okay, so you're gonna roll it up. When you're rolling it, oops, sorry. You don't have to roll like, you don't have to roll really slow. You can roll, don't whip it, but keep it on the table. I don't want it to bounce. So just like a nice, smooth, look fast. Maybe you want to go off this side of the table so we can try to see this. You went a little early. Try it. What do you think I'm trying to get to happen? What do you think should happen? Ball? Yeah, it should reach the ground at the same time theoretically. And if we do it where his timing is right, it'll work. Verti's a little bit faster. Ooh. Did you hear only one bounce there? Isn't that kind of amazing to think about? So Rachel, think about this, right? If I extrapolate this idea, if I take a bow and arrow, right, and I pull back on the bow and arrow and I let go, and then I take a BB gun and shoot them at the exact same height and both horizontally, they both hit the ground at the same time. Cool. I mean, obviously with their resistance things will change, but theoretically speaking, if an object is launched horizontally, another one is dropped, they act the exact same way. The time taken is identical. So we're going to take this idea and we're going to use this in one of our problems in a minute. And that's what this diagram is trying to show you here. So Jake would be the red ball that's falling down. That would be like a free fall. And at the same time, Mike launched his horizontally. And what they noticed, and you could actually buy something to do this. You could have something like a spring-loaded thing and launch it at the exact same time. You let go, and you would see this happen like that. But that was the same idea as what's happening. And every instant in time, notice that these all line up. The ball is at the exact same height every single time a snapshot is taken along the way. Okay, thanks guys. Okay. Very simple, but it's something that we're going to need to know. So we have to utilize that idea. So, keeping that in mind, let's take a look at our first example. Okay, let's go to the next slide and look at the first example there. By the way, it works so much better in this class than the other class. We couldn't get it. It was always like off, like the ball, like boop, 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 boop. There was like a small discrepancy in it. So you guys got it on the second try. That was good. Very good. So let's say we're looking at a bridge, okay, and it's 300 meters above the ground, and we've got Tom Cruise. He's in another movie that he's starring in. Who knows what it is this time? And he's in this sticky situation, meaning he's got to get away from these people that are chasing him. And he's on the bridge, and he decides he's just going to run off the bridge.
Jump.
Not even jump, just run right off. he realized, he's like, I'm really good at physics, I can figure this out. And I see there's like a platform that's floating, and it happens to be a bouncy castle. And he's like, I want to land on that so I don't get hurt. Floating in the river. So he runs off with only horizontal velocity. Okay? So I wrote he jumps off the bridge, but by running off the edge only in the horizontal direction. So like the tennis ball that Mike just rolled across the table. That's Tom Cruise running off the bridge, just running straight off. He hits the water, and after a horizontal displacement of 50 meters, okay, so he's fallen down 300 meters, and he's gone horizontally 50 meters. And we want to figure out what the velocity is with which he jumps or runs off the bridge. I should say runs instead of jumps. Okay, what is the velocity with which he ran off the bridge? With which he ran, I should correct that for next year too. Ran off the bridge. All right? So, what do we know in this problem? What is something that's given? And you have to consider the vertical and horizontal as different things, so specify when you give me answers. Jen, what's one thing you know?
You have VIY, which is 3 hoops. Am I too far ahead? 300 meters?
You have y.
Yeah.
You said VIY, just y. That's all you have right now is y. So you have y, and what is y equal to? It's not 300 meters, be careful. Yeah, it's negative 300 meters. Let's remember the negative. Simply because Tom Cruise is falling down toward the river, not up. Okay, so the displacement vertically is negative 300. Good, that's one piece. And what else do I have?
We know the it's like calling that.
What is it?
Negative 9.81.
I'm going to put AY for acceleration in the y direction. And very good, Victoria. Negative 9.81 meters per second squared. Good, good, good. I know something else. What else? There's another number in the problem. Figure out what it means.
X is 50.
Yep. His horizontal displacement is 50 meters. Okay, let me draw you a quick diagram in case you're confused as to what's happening. So here's the platform. Here's the water. Okay, this is a suspension bridge. Make-believe cables are holding it up. Here's Tom Cruise, modeled as a point in space. He runs off the edge of it, and as a result, ends up falling 300 meters, but ends up going out this way, 50 meters. Trying to make it out the door, sneeze, or not sneezing. All right, so he moves out 50 meters and down 300 meters afterward. That's really all we know right now. There's one other piece of information I want to discuss, but I haven't really gone over yet. Remember what we said about air resistance? We consider it to be, what's the word? Negligible, doesn't really affect the problem. Now, air resistance in these problems would give you some sort of horizontal acceleration. If I'm running, right, and there's a wind that pushes me back, wouldn't that be like a negative acceleration? Or if I'm running down the street and there's a wind behind me, that's like a positive acceleration pushing me. But we're assuming there's no air resistance. So what would the acceleration be in the x direction if there's no air resistance? Yeah, it'd be 0. So here's an amazing thing that we're going to notice this year. Every time we solve a projectile motion problem, we will always use the same formula in the x direction. What formula is the only formula, the only one, that involves no acceleration? There's only one formula that doesn't have acceleration in it, that we've learned so far, obviously. The first one that we did this year didn't have acceleration. What was it? Close, not V over.
Or V is equal to X over T.
Yes, V equals X over T. So we don't know what formulas we're going to use in the Y direction yet, but I definitely know in the X direction, it's going to be something with X over T. 1 second. And let's just call this VIX for now, meaning the velocity in the X direction. Okay, I'm going to pause there, okay, where Tom Cruise jumped off the bridge by running straight off. And he ran for, in a horizontal direction, and he ended up 50 meters out from the bridge, and he had fallen 300 meters down, so we listed those givens, okay? Now, since he ran off the bridge horizontally, and he didn't jump vertically, what would VIY be? Because he's only running horizontally. It'd be 0, good. Because remember yesterday with the tennis ball, where if we drop the tennis ball, or if we roll the other one horizontally, they hit the ground at the same time. So whenever an object is only launched horizontally, it's like a free fall. So VIY is 0. Now, we're trying to find the initial velocity, which is Vix in this case, because he's only running horizontally. That's our goal. But we can't do that. The bottom formula here that's listed that we're always going to use in the x direction, as we mentioned yesterday, we can't find Vix because we don't have time. We've got the displacement x, that's 50 meters, but I don't have the time. So anybody have an idea to how we can maybe find the time if it's useless in the x direction? What can we try and do? This is tough. It's not an easy way to do this. Remember, think back to the tennis balls. If one was rolled horizontally and one was dropped, they took the same time to hit the ground, didn't they? Yeah. So couldn't I just look at the y direction and consider this problem like a free fall and find the time it takes? Because the time it takes to fall 300 meters if I just drop something, instead of Tom Cruise running out this way, is the exact same time. So I can only look in the y direction if I want to and find the time. And then I can take that time and use it in the x direction. The reason this works is we call t what's called a linking variable. It links the two directions together. Maybe I'm running this way and it's all horizontal. But the time it takes to do something doesn't matter whether you're horizontal or vertical. Time is time. It doesn't matter which direction you're looking in. So although we split this problem into two directions to start, when we find the time in either direction, we can use it in either direction. So if I were able to find the time in the y direction, let's just use it in the x direction. So in the y direction, if I'm trying to find the time, how can I go about doing that? What formula might I use that involves time? You have three choices, remember. Three choices. One of them does not have time in it, so that's out of the choices. So you really only have two choices left for that direction.
Isn't it VIT plus 1/2 AT squared?
There it is. Good. Good, good. AT squared. Now, I'm going to put little subscripts in again. Remember, I'm going to put these little subscripts in to indicate them in the y direction. They're not variables. Those little y's that I just drew in right there. This is not a variable. This is not a variable. It's a subscript indicating I'm talking about the velocity in the y direction, the acceleration in the y direction. But what's VIY? What did we say the velocity was in the y direction to start? It's just 0, so this part doesn't really matter. Remember, this just goes to 0. But that arrow to 0 showing it's going to 0. So it turns out that in the y direction, my formula is actually quite simple. Okay, it's 1/2 AT squared. Oof, thank you. It's 1/2 AT squared. So, I can try and determine the time in this problem. Solve for it algebraically. How do you get rid of a 1/2?
Y by 2.
Yup. How do I get rid of the A? How do I get rid of the A? The acceleration. Divide by A. So let's multiply by 2, making this 2y equals a t squared. Then divide by A. Giving me t squared equals 2y over A. Now I take the square root. So it's 2y over A underneath a radical. Why don't I need the plus or minus this time? Can somebody explain that?
Because time can't be negative.
Good. Time can't be negative. Okay? We're looking at time being positive. So take 2 times the negative 300. Divide that by negative 9.81. And take the square root of that to give us the time it takes Tom Cruise to hit the water. Again, 2 times negative 300 over negative 9.81 under the square root. Jake,
61.2.
take the square root. Did you take the square root?
Nope.
So take the per second square root, second answer. So take the square root of the previous answer that way. What do you got, Jake?
7.8.
That's it. 7.8 seconds it takes Tom Cruise to hit the water. Now, this is as if he was just dropped. Remember, now we're looking as if Tom Cruise was just falling as a free fall from that 300-meter distance. But he's not just falling, he's running horizontally like this. So in the time that he's falling, he's also moving this way. Again, it's like if I was an airplane going like this, right? If I let go, when I let go here, it doesn't fall straight down, it falls this way. So Tom Cruise is not really falling straight down, he's moving to the left or right. So it turns out that we could use that time it takes to fall as the same time it would take him on the left-hand side. So take this quantity and use it for t. This is our linking variable, because it links the two equations together. It's the linking variable. You can use it in both directions always. So let's go ahead. X was 50 meters. That's how far Tom Cruise was able to move horizontally after he ran off the bridge. And it took him 7.8 seconds to hit the water. So we can determine the velocity he needed to do that by dividing those two quantities. 50 over 7.8 gives us 6.4 meters per second. So again, if Tom Cruise or if an object had just fallen, that's how long it would have taken. But he was running horizontally. It still takes that long, but in that time, he was able to cover 50 meters outward. Okay, outward.
In every problem, should we solve for y first and then link?
It depends on the problem. Sometimes you'll have enough information in the x direction to find time, and then you might need to use it in the y direction, or vice versa. Okay? It depends on the problem, Jake. So let's look at the next problem to see what I'm talking about here. What's it called? A plane or a bomber, really, that's delivering a package to a remote island. So if I'm a plane, watch my hand, and I'm flying, and I drop a package, it doesn't fall straight down, right? Again, it falls outward like a parabola, as if it's being launched horizontally. And you've seen this before if you think about it, and you should never do this. But if you did ever throw something out the window, like a piece of gum or something when you're in a moving car, it doesn't move like that. It gets pulled back. It starts to move with you, but it curls. It doesn't actually move in a straight line. It's the same thing. If something moving across the air were to just drop something, it moves like that. It doesn't fall straight down, obviously. So in this problem, what we're trying to do is this. We're told that this plane is flying 500 meters above the ground. It has to drop a package. We know the plane travels at 607 kilometers an hour, or 186 meters per second. So we want to know how long it's going to take to hit the ground, and how far away should it be from the island before it drops, right? How far will the package travel horizontally? So this plane needs to know, and this was really important in like World War I and World War II, when they had to drop off med kits and medical packages and food supplies. The plane would need to know, okay, I'm at the right location, drop it now. And the package would fall like this and land in the appropriate landing zone. So we're trying to determine how far is this package going to move horizontally once it's released. It releases and it falls. How far is that so we know how far back the plane needs to know when to drop the package and how long it will take to hit the ground. So it's a very similar problem than the last one. It's almost identical actually, except now we don't know VIX. We don't know the speed Tom Cruise is running at. We're trying to figure out in this case, in this problem, the displacement instead. Give me a second. We have exams, so we have 3 minutes. Can I keep going? Okay. I don't want to make you watch this tonight. I'd rather get through it today. So X is the unknown that we're trying to figure out, how far the plane should be away from the island, or how far the package would travel horizontally. We know the velocity of the plane this time, 186 meters per second. We don't know the time it takes, so we can't do much in the x direction again right now for this problem, because we're missing those two variables. Okay, we're missing both of them, and this would be our equation we're going to use, but I don't know x and I don't know time, so it's not enough information. Let's go to the y direction. We know it's going to fall a distance or displacement of negative 500 meters, because the plane is flying at an altitude of 500 meters. We always know the acceleration in the y direction is negative 9.81 meters per second squared. Again, we know VIY is still 0. It's always going to be 0 when the object is launched horizontally. Always. Okay, tomorrow when we do problems with this, you're going to see that it's always 0 when it's launched horizontally. And we'll figure out the time in the y direction. It's the same exact problem in the y direction. It's identical, just different numbers. So we're going to use the same exact formula. Now, again, VIY is 0. I can cancel that part. And if I solve this for time, it's the same solution. That's why I have you guys solve generically so you can see this. Time is the same thing. Radical 2y over a. It's the exact same expression that we had for the Tom Cruise problem for time. It's not changing at all. So we take 2 times negative 500 meters over the negative 9.81 and take the square root of that answer to figure out the time it takes this object to land from a height of 500 meters when it's dropped.